Okay, so next we are looking at the extended product rule, which is, again, it's what happens when you take the derivative of multiple functions times each other. So when we did two functions, right, it was f prime g plus g prime f. When we add a third function, basically you're now going to have three chunks. Each chunk is going to have a different prime, but all chunks are going to have the same three functions. It's FGH, FGH, FGH. And this says P, but that's definitely a mistake. Just correct that. It shouldn't say P. Okay, so FGH, 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 and then you just put a prime in a different spot in each one. So it's like FGH plus FGH plus FGH, and then I go, okay, in the first one I'll make F prime, in the second one I'll make G prime, in the third one I'll make H prime, and that's it. So, again, not super difficult. You just make sure that you, go through and make sure that, it's the same product every time with a different section is the derivative. So for this one, what we're going to do is just take a different derivative each time. And the first one we have f prime and g prime and h prime. Okay, so in the first one, let's take the derivative of f. The derivative of the x is just 1. So we get x squared plus x times x minus 1. We move on to the second one. We write f, which is x, g prime, which is 2x plus 1, and then h, which is x minus 1. We move on to the third one. We write f, which is x, g, which is x squared plus x, and then the derivative of that last bracket is of course just 1, so I don't do anything. So your derivative here, y prime, is just given by this. Now again, you might be asked to clean this up. What you would do is you would FOIL it out and then collect the like terms, but for now let's just leave it like this. Some of the test questions will ask you to simplify, other ones will specifically tell you not to simplify because at some point this becomes more trouble than it's worth. Now you can use this idea to actually get the power of a function rule. Okay, so let's imagine, for example, we had x plus, let's say we had 2x plus 1 to the power of 5, and we wanted to take the derivative of that, right? That's the same thing as 2x plus 1, 5 times. Now, think about what we just said about how this would, you would take the derivative of this, right? You would basically write this out 5 times, and each time you would take the derivative of one of these different brackets. Of course, every one of these brackets have the same derivative. So what you would get is like, you would get, first you would get this one is a 2, then you would get the second one is a 2, right? Then you would get the third one is the 2, right? And so you kind of see what's happening here, right? You would basically get this 5 times. Now what is this? Let's write this out now. We have 5 times this happened, and then we have 2x plus 1 to the power of 4, and then we have it times 2. Now look at what this is. The 5 is the exponent, which comes to the front. The 2x plus 1 is repeated exactly as it was in the question, and then the 5 drops down to a 4. Then what we did is we took the derivative of this bracket, which the 2x plus 1, the derivative was 2, and that sticks on at the end. So this is where they're coming, this is what this means, okay? The n comes to the front, then you have g of x exactly as it was with no changes to the power of n minus 1, and then you kick out the derivative g prime, which comes at the very end. Okay? And that's how you take the power of a function. So let's try this in an example here. So it says y equals x squared minus 2x to the power of 10. Okay? So again, if we were to write this in the form y equals gx to the power of 10, right? Then we know that y prime is equal to 10 times g of x, right, to the power of 9, and then times g prime. That's the way this works, okay? So bring it down, drop the exponent, same as yesterday, then take the derivative of whatever was inside that bracket. So let's try this here. To do this one, right, y prime is equal to 10 comes down, x squared minus 2x is copied exactly out as it was before, to the power of 9, right, instead of 10. Then you take the derivative, 2x minus 2. Okay, and that's your answer. Now, these ones are good examples of where you are not simplifying this, right? It's easier to understand this in factored form than it would be in simplified form. Just to demonstrate that, let's take this question. So let's just make a new sheet here quickly. So x squared minus 2x to the power of 10. If we get the derivative of this, right, I mean, this is not simple or useful particularly, right? For one, it takes, anyway, yeah, I think you get my point. Not very simple. It's far easier to just think of this as what you see here, right? Leave it unsimplified. Now, remember what this Leibniz notation means, right? It means find the derivative of y when x is equal to 1. So then what I'm going to do is I'm going to do y prime at x equals 1, and we get 10, 1 minus 2 to the power of 9 times 2 minus 2, right? And of course I can look at that and realize that this has a derivative of y prime equals 0 when x equals 1. Can double check that here, and I go f prime of 1 should give me 0. On the graph, I should actually see a turning point at 1. Let's get rid of the derivative here, which I do, right? I see a flat tangent there, which is consistent with the idea that the slope when x is 1 is actually 0, which is what we found. Okay, let's try one that's bringing all of this stuff together. Okay, so this is a good example of like a more complicated question that's asking you to do both of these skills at the same time. Again, let's define it as f of x, or let's do it the other way. H of x equals g times f. Okay, I'm going to say g of x is equal to, so my first puzzle piece is g, x squared plus 2 to the power of 5. My second puzzle piece is f, which is x squared plus 3 to the power of 2. Okay, now I'm finding the other parts, g prime. Okay, bring the 5 down in front. X squared plus 2 copied out to the power of 4. Then I take the derivative of what's inside the bracket. What's inside the bracket, the x squared becomes 2x, the 2 becomes 0. So there's my derivative of g prime. Now I make the derivative of f prime. The 2 comes to the front. X squared plus 3 is now only to the power of 1, so I'm not going to write anything. And then I'm going to write 2x because once again, the derivative inside there is a 2x. Now, when I go to write h prime, I know that h prime is gf plus gf with a different prime on each one. So let's put the prime on the g and then the prime on the f. Okay? And now I just put the puzzle pieces together. So I start with g prime. 5 x squared plus 2 to the power of 4 times 2x. Okay, the next puzzle piece is f, which is x squared plus 3 squared. Then I have plus. The next puzzle piece is g, x squared plus 2 to the power of 5. The final puzzle piece is f prime. 2, x squared plus 3, 2x. Okay, that's all the pieces that we have. And that is the derivative. Again, you will not be asked to simplify something like this because it is tedious beyond belief. Let's check to make sure that we did it right here. So let's go and write the different things that I said. So I said g of x was x squared plus 2 to the power of 5. I said f of x was x squared plus 3 squared. I said h of x was f times g. When I take the derivative of h, Again, GeoGebra is going to expand and simplify that derivative, so I don't want to do that. So let's compare that to what we did. Let's do the derivative of f and the derivative of g. I didn't spell that right. Derivative. Okay. Derivative of f, derivative of g. And then let's do f prime g. That's right, g prime f plus f prime g. Sorry, you're going to have to actually multiply those. We get that. Yeah, see, I guess I should have thought this through. It's expanding it again, so I guess I could do h prime minus p and simplify. And it is 0. This is not really great proof of what we did. I guess I could type in what we did, but hopefully you kind of followed what I did there. When it took the derivative here, it expanded it all out. And what I then did is I subtracted this by the other expanded derivative, and it gives you 0. So they are, in fact, the same. Not too easy to check your work on these ones, unfortunately. So that's why I suggest this sort of puzzle piece method. At least it shows me what you were trying to do, and if you make that small mistake, I can still kind of work on. I know that you know what you're doing. You just made a small error. Okay, find the slope of the tangent to each curve we need to do, and then we have one last application question here. So this first one, again, this question is really the exact same as the one we just did. You know, it's you know, do the same thing and plug in the 1. I'm going to leave that to you, and then if you want to check your answer, you know, we can check with each other or put it into GeoGebra and see if you got it right. I do want to walk through how to do 2 with you though, because 2 actually, you know, it doesn't look like a product, right? It looks like a quotient. It looks like we're dividing things. So let me show you how you would do 2. So here we have f of x is equal to 2x plus 5. And now what we're going to do is we're going to change it into multiplication to the power with using a -1 power to bring that denominator back up to the top. Okay, so you can see what I've done here. I'm going to say my g of x is 2x plus 5. My h of x is 3x minus 1 to the power of -1. And now it really is a product, right? It's this g function times this h function, just remembering that this -1 is part of the h function because I'm bringing h off of the denominator to bring it up to the numerator, right? That's what a -1 exponent does, right? It flips you from numerator to denominator or vice versa. Derivative of g here is really easy. It's just the 2, right? 2x becomes 2, 5 becomes 0. Derivative of h is a little bit trickier, so let's follow carefully with h. Bring the -1 down. Do 3x minus 1, drop the -1 to a -2, and then take the derivative of the bracket, which is a 3. H prime, you know, if you want, you can write it like this instead, where you're writing, just get a fraction bar here. So what would be in my numerator here? A -3 would be in my numerator. A 3x minus 1 squared would be in my denominator, right? That's what h prime would look like if you're writing it in fraction form. It's okay to leave it in a negative exponent form. It's up to you. Okay, I know the derivative of f would be g, or hg plus hg with a different prime on each one. So let's put the prime on the g there and the prime on the h there. And then I write f prime is equal to, and I'm just going to write out all the puzzle pieces that I had. So, a -3 over a 3x minus 1 squared is h prime. Then I have g, which is 2x plus 5. Then I have add, okay, h of x, which is 3x minus 1 in the denominator. So let's just do it as a fraction again. I have 1 over 3x minus 1, and then this is multiplied by the derivative of g, which is just the 2. So you can clean this up a little bit without too much difficulty, right? Where you're going to say this is -3 bracket 2x plus 5, and then 3x minus 1 squared on the bottom, and then this is